Well, good morning, good afternoon, everyone. Thanks for overcoming the Zoom update and being able to make it here to the AGN seminar this morning. So it is my pleasure to introduce Dr. Yiqing Song, who is currently an ESO fellow in Chile and an expert of radio studies of LIRGs and ULIRGs, among other things. Yiqing received the PhD from the University of Virginia last August, working with Aaron Evans and the GOES collaboration, which in my very unbiased opinion is a fabulous collaboration that turns out a lot of good PhDs. Yiqing was a Grote River doctoral fellow at NRAO, and now, and before that, they got the bachelor's degree in physics from UCLA, working with Gene Turner. And I'm sorry, I'm out of breath because I was just walking all around, but it's not me that you need to listen to. So Yiqing, the floor is yours. Thank you.
Thank you much. Thank you very much, Vivian, for the introduction. And thank you everyone for tuning in. And so first, before I start, I want to say that all of this that I'm doing with the radio, with the VLA, is actually started as a project focusing on star formation. So AGN is something I kind of like stumble upon later. And I'm very excited to be here for that reason, because you all are AGN experts. And I really hope that throughout this talk that could give you, I guess, some perspective from, a person who's been studying star formation. And also I'm hoping to get some feedback on what you think that will be interesting follow-up on the AGN side. So off I go. So I will be talking about ultra-luminous and luminous infrared galaxies in the local universe, as Vivian already mentioned. And this project is part of the VLA survey that we've been conducting as part of the Great Observatory All-Sky LIRG survey. And so first, introduction to LIRGs and ULIRGs. Just for those who are not familiar with the terms, that luminous infrared galaxies and ultra-luminous infrared galaxies are these galaxies that are very luminous in the infrared. And so here are some of the definitions. But most importantly, these systems, when we go towards a higher redshift, about 1 to 2, that's when galaxy assembly are most active, when we have a lot of star formation and aging accretion going on. These are the galaxies that actually dominate the contributions to the co-moving star formation rate density at this peak era of galaxy growth. Now, looking into, just zooming into the local universe, these systems are actually pretty rare. But deep optical observation have shown that they are primarily interacting and merging gas-rich galaxies. And so during this interaction, as you can see, this simulation here, gases funnel toward the center of these galaxies, trigger very active nuclear starburst, which makes them almost exclusively all starburst galaxies, meaning that they all lie above this star formation main sequence that we know about, that's spanned by these normal spiral galaxies, star-forming galaxies. And also via multi-wavelength observations, we also find that many of these local LIRGs and ULIRGs host AGN. For example, this merging system NGC 6240 via hard ray observation, people have found these two very powerful accreting supermassive black hole in the very center of these merging system. So combining all of these information, local LIRGs could be representing this phase of major transformation that many massive galaxies may have gone through in earlier time of the universe, but we can't really study them due to their far distance. So these local LIRGs provide a very good opportunity in the local universe for us to conduct detailed study of this host and supermassive black hole co-evolution before that precedes the formation of luminous quasars and red and dead elliptical galaxies. So these galaxies are interesting places to conduct these studies, but also what makes them bright in infrared so prevents us from knowing or conduct very comprehensive or conduct a detailed study of the most energetic regions that's powering their extreme activities. So here shown is an example of a local LIRG BB114. This is a color composite image from HST, where you can see all the UV and optical light from the young stars outshines the entire, basically from the Western component of these emergent system. When we have dust in the system, this dust would absorb the UV and optical light and re-emit the energy in the infrared regime when we have these infrared emission. And when you have a lot of dust, what happens is that the dust absorbs almost all the UV and optical photons from these whatever activity that's going on, and then they are then basically in these systems we have these infrared emission that's completely dominating the energy output of the SED or the total energy of these systems. Now, this makes it difficult to study what is actually giving rise to these very bright or luminous or very extreme activity that's powering these high infrared luminosity. Is it AGN or is it starburst? And so to investigate the activity in these systems in a more comprehensive way, we need all the information that we can get from all the wavelengths. So here I'm showing the same galaxy, but with the observation from X-ray to far infrared. And you can see that from shorter wavelengths to longer wavelengths, you see the energy dominating component shift towards the eastern component, which is actually the component that's powering most of the emission that's in the system. And so this is what motivates the Great Observatory All-Sky LIRG survey. And so this is a multi-wavelengths campaign with international collaborations from people working all over the place in the world to study to provide a comprehensive multi-wavelengths aspects of the activity, AGN or starburst, that's going on in all the local LIRGs and ULIRGs that's been discovered in the IRAS revised bright galaxy sample. And so I'm not the first one to be speaking in the AGN seminar. Of course, we have Vivian and some other people from the team who've been focusing on looking at these systems and AGN these systems in the infrared regime, specifically in the near infrared and mid infrared. And now we have JWST data, and this is also a really great place where we can isolate or a really great tool where we can isolate the energetically dominant component. But today I am mainly talking about the radio aspect. Why radio? So radio is largely unaffected by dust extinction, and that will allow us to provide or to see through all the dust and provide a direct view into the most energetic regions that's powering these systems. So here I'm showing an older radio image from Condon et al. 1991 at 1 gigahertz. And so you can see the gigahertz emission is tracing the far infrared very well, and it's highlighting this really energetic eastern component very well as well. And at gigahertz radio wavelengths, we are mainly looking at two components. One is synchrotron, the other one is thermal free emission. So synchrotron emission is basically when you have electrons and they're accelerated by some magnetic fields, and then they emit photons that way. And then thermal free emission is when electrons are interacting or in a thermalized ionized plasma, and then they interact with ions and emit photon that way. And these two components have distinct spectral features or spectral shapes, and that allow us to basically isolate or identify what is or to separate these two components when we have a good frequency coverage. But the picture is a little complicated when we want to know what is actually providing the synchrotron or the thermal free emission. And so because synchrotron, we can have magnetic fields in supernovae or AGN, and the thermal free, we can also have these ionized plasma near the AGN or also in massive young, around massive young stars and H2 regions as well. And so separating what is the component that is dominant at gigahertz emission, and also where each of the components coming from, becomes a little bit difficult, even though radio is a really great tool for probing these dusty regions. So on galaxy scales, people have found these, very well established relation between the 1 gigahertz and far infrared radio emission. And far infrared is tracing the cool dust that's heated by the star forming activity. So this points to a shared origin of the radio and far infrared star formation. And this relation also allows to be able to identify radio loud AGN, which has these very synchrotron dominated axis radio emission coming from these large scale jets or winds. But when we look at the radio quiet AGN, as I mentioned before, it becomes a little bit more complicated because the radio emission that we're looking at could be coming from star formation or various other mechanisms that's associated with AGN activity at various spatial scales as well. And so in terms of local LIRGs, people have been using high brightness temperature as an argument to find AGN or identify AGN in the radio regime, or also using a spatially resolved spectral index map. So basically looking at where AGN or where the steep spectrum or flat spectrum component may be dominating. And so these have some of the past works using VLA that people have been done in the local LIRGs to look at or to search for AGN in these systems. So all of this is just to show that, in order to use radio as a probe for the activity that's embedded in these very dusty and powerful systems, we need really good frequency coverage and also spatial resolution, or the ability to resolve the structures that we're seeing. So this is provided by us by the upgrade Jansky Very Large Array, which has a very wide frequency coverage from 1 all the way to 50 gigahertz. And it's got also a very good sensitivity with this upgraded bandwidth. And with all these different configurations, we can image the structure and different scales to probe, physical scales to probe the emission coming from the most compact or also the most diffuse regions as well. And this motivates the survey that we have as part of the goals campaign using the VLA. So here we have chosen a sample of about 70 galaxies from the full goals sample that span the declination range plus minus 20, so called equatorial. And so this selection is basically chosen so that we can do follow-up studies with facilities from both northern and southern hemisphere. And also, as you can see from this plot, that the sample here span the entire infrared and distance range, infrared luminosity and distance range that's spanned by the whole full gold sample. And it also samples the various merger stages that's represented in the gold sample as well. And in order to be able to at least to the first order separate the non-thermal or the synchrotron and thermal free emission, we also have these multi-frequencies set up from 3 gigahertz to 33 gigahertz on the low and then high end, so that we can try to map the how the spectral indices varies in the different system, and also regards to their relative location in the system. And as I mentioned, the VLA is able to provide these view at a different for different physical structures at a different physical scales. And so we're using a multi-configuration strategy to observe these systems. On top of these 3 different frequencies, we also observe them with the different configurations so that we can get a view of the radio emission distribution on both kiloparsec and also 100 parsec scales. And you can see on 100 parsec scale, we're really isolating the most compact energetic regions in the eastern component. And we can resolve them into this individual very compact knots here. And so first, I want to just take a step back and talk about what we've learned from the lower resolution lower resolution component of the survey. That sample is a little bit more diffuse, more comprehensive view, I guess, of the radio emission of these regions. And because of the lower resolution, and then they're able to sample the emission from larger scales, we can compare them with infrared maps, which have roughly 6 to 7 arcsecond resolution from Herschel. And so we have these 3 different frequencies, and we also have maps at 24, 70, and 100 micron from Spitzer and Herschel, so we can make a comparison to see whether on this roughly 10 kiloparsec scales, if we see something that's interesting, whether the radio is correlating with infrared emission and how well they correlate. And to do that, we also want to see whether these regions that's represented or potentially powered by different mechanisms show different radio and infrared correlation. And to do that, we've mainly utilized the multi-wavelength AGN classification from the literature. So that involves X-ray and optical and mid-infrared mainly, and sometimes radio as well. And because of most systems are unresolved and they're very compact system, unresolved on 10 kiloparsecs, using this multi-wavelength AGN classification, we're able to separate these blobs, I guess, into 3 different categories of AGN and composite nuclei. That's a mixture of AGN starburst activity and or also just a starburst system. And some of the systems that are nearby is resolved, and using on top of these classification, we're also being able to identify some of the star-forming clumps that's outside the nuclear area in the more extended disk regions. And then we can also try to see if these relation that's spanned by the star-forming clump is different from the AGN or the nuclei. And so here is what we have. So we looked at the correlation for all of these structures where the component that we've identified and classified in the 3 different radio bands, and then compared their radio emission to the ones we see or measure from the mid-infrared and far infrared. And as we can see that all the regions, at least at 24 micron, we don't really see a clear difference, right? At 24 micron, the AGN, the star-forming clumps, and the other types of nuclei, they seem to lie pretty well on this like very tight relation between the radio and the 24 micron emission. And the AGN really start to pop out when we go down or we go up towards longer wavelengths when the emission is more dominated by the cool dust rather than the hot dust emission. And also we notice that the AGN are more distinct when we look at lower radio frequency compared to the higher radio frequency. And so this makes sense when we especially look at how the spectral shape behave for these different type of regions that we've classified. So on this 7 arcsecond resolution or 10 kiloparsec roughly scales, we see that the AGN have a pretty steep spectrum at roughly 0.7 all the way from 3 to 33. And the star formation have a slightly flatter spectral index from 3 to 33, which means that the AGN is more dominated by synchrotron emission at all frequencies, basically. And that's why we see the AGN is popping up at lower frequency. That makes sense. And so we can also, because here we're trying to compare with infrared emission, but also the spectral shape, we have matched resolution 3 to 33 radio continuum observations at about kiloparsec scale as well. So here we're resolving more of the structure compared to the 10 kiloparsec, but still preserving some of the more diffused emission. And we can make a comparison just for these radio frequency as well. And so here I'm showing this NGC 6240 again, where we can see the radial bubbles from this dual AGN is really popping up at 3 gigahertz, where it's synchrotron dominated. And here, interestingly, we can see that when we zoom into the kiloparsec scale, the AGN star formations share the similar median spectral indices, also around 0.7 at a lower frequency end, meaning both at this frequency range, they are similarly dominated by synchrotron emission. But when we go towards higher frequency, towards the 33 gigahertz, we see a clear distinction between the AGN and star forming activity, where star forming clumps are really flattening out in terms of spectral shape towards higher frequency, meaning that we are really seeing for the star formation that thermal free emission from these H2 regions are actively dominating the spectra for these systems or for these structures. Okay, now here are the low resolution side. And we also have these high resolution measurements were the observations that we can utilize to further characterize in detail what is happening in the central kiloparsec of these very extreme systems. So here I'm just showing some of the images from the high resolution side at 15 or 33 gigahertz. You can see this radial morphology in the central kiloparsec is really varied. And here I'm also showing two very well-known AGN. On the lower left, agency 1068, where you see the jet structure, and also in upper right, NGC 7674, where you also see this elongated linear jet structure that's powered by the central AGN. So characterizing these regions is, as you can see, slightly more complicated than when we look at the lower resolution when things are just big blobs. Here we need to be more careful to identify the most compact and brightest region that separate that from the diffuse emission underlying it. And so to do that, we are using this Python program called AstroDendro, which is very popular right now, and which is a program that's basically designed to identify the hierarchical structures in an astronomical image, and you can into this tree-like structure, so that allow us to identify the most bright and the most compact regions, or the leaf-like structure in these systems. And these are the ones we'll be focusing on. And so using this method, we've identified about 100 regions in our sample that have average sizes of 100 parsec. And so using AstroDendro, we're able to also, aside from
Yiqing, are you still there? Oop. I guess it's Yiqing who lost. No worries. I was wondering if it's me who lost it, my internet, or you, but okay.
I think, yeah, the internet is a little unstable here. Sorry. But yeah, continue on.
Can you go back a slide?
This one.
Yeah.
Okay, I don't know where I dropped.
I think I got to the point where you talk about the leaves and using that to identify structures. Yeah, so middle of the slide. Yeah.
Okay.
Thanks.
Yes. Yeah. So that's basically it about the slides. And so basically using AstroDendro, we're able to identify the most bright and compact regions in the nuclear structure that we see in these systems with our 15 or 33 gigahertz high resolution continuum map. And we're able to characterize the size and also luminosity as well. And we can make the comparison between luminosity and size. And so we see that the luminosity at 33 kind of scale linearly with the size, which is what we expect because I realized I think maybe my video is not on. Sorry. I don't
No
know
worries.
yeah,
okay. Your video isn't on, but yeah, that's fine.
I don't know what's happened.
That's okay if you want to keep going with, yeah, there you
okay.
go.
Yes, sorry. Yeah. Yes, so this is what we expect the trend with the size because we have, as we see early on in the distribution of the distance of the sample, that there's a wide range of distance. So when we go towards further distance, we're getting larger sizes and also including more light in what we're measuring. So this is expected. But we can also see that at any given sizes, there are regions that are or appear to be brighter. They have higher luminosity and higher luminosity surface density compared to some of the other regions. And so this is interesting, and we want to investigate what is actually causing the elevated radio emission in these brighter regions or more energetic regions. So to do that, we basically repeat the exercise we've done before. So we have the multi-wavelength agent diagnostic for the host galaxy, and that's something we can use if we can identify whether a region is actually the nucleus. And so that is the more complicated part. And to do that, we need to know where the region is located and whether it is the nucleus. And we utilize archival high-resolution multi-wavelength data set wherever we can find from HIC or from ALMA to try to see where are these regions and whether they could be the nucleus of the system. And this seems to, it sounds maybe a very simple task, but because they're mergers, it becomes a little bit more complicated when we're trying to consider, there might be a second or third nucleus. And so here I'm showing some example. The top panels is basically when we compare the radio to the HST, we can distinguish the off-nuclear star-forming clumps from the actual nucleus using the morphology that we have identified using with HST or at other wavelengths. And so with the multi-wavelength agent diagnostic that we've done before, or we've collected before for the host galaxies, now we can identify that this off-nuclear region, it's a star-forming clump on a spiral arm, and the nucleus is a composite nuclei. And for the AGN, it's a little bit more straightforward because we see this jet structure, and with the spectral index map that's spatially resolved, we can identify where the AGN actually is, where that usually shows this synchrotron self-absorbed flat spectrum compared to these synchrotron-dominated jet structure. So after we've done these classifications for all of our 100 sources, here's what we see. And so we're seeing the regions with elevated emission are either known AGN or the nuclei that's considered to have some AGN contribution or mixture of both AGN and starburst activity. So the question we want to ask here is, okay, so we have these nuclei that could be powered, that are powered by AGN, could be powered by AGN, and they have higher radioluminosity compared to the star-forming regions. Are these nuclei then powered by AGN activity? And that's what's driving their elevated radio emission that we see. And to investigate that, we did some tests. And so first we look at the brightness temperature argument, or a brightness temperature of this individual sources to see whether we see this extremely high brightness that it's coming from a non-starburst origin. But we did not find a very high brightness temperature for not either for none of those sources, they have high brightness temperature. But we do notice that, I mean, this is also the brightness temperature also scales with the luminosity and surface density that we're measuring. So it makes sense that the AGN and the AGN starburst nuclei show this higher brightness temperature. But here is inconclusive to say whether, you know, these mixture or this composite nuclei is actually powered by AGN activity. And then we compared with the X-ray luminosity. The X-ray is considered, you know, to be coming from AGN emissions in AGN coming from AGN emission. And so what we can see here is that going towards higher radioluminosity, we do have overall higher observed X-ray volumetric luminosity as well. And we do see that some of the already identified AGN lie in this radial quiet regime between the X-ray and the radioluminosity. But also we do see that some of the composite nuclei lie on this relation between radio and X-ray that's defined for the star-forming galaxy as well. And so there are two possibilities, is that, okay, these nuclei could just be powered by star formation and there's no AGN contribution, or that they could be, there could be AGN contribution, but because we're looking at the observed luminosity, but not intrinsic X-ray luminosity, the X-ray is also diminished because of some foreground dust extinction that does not bring these points up to where the AGN should be. And when we look at when we compare the radial luminosity to the infrared diagnostics, this is kind of in line with what we see in X-ray, is that all these brightest or nuclei with the highest radioluminosity also have the steeper mid-infrared, which means that they have higher luminosity, they have higher flux at 30 micron compared to 15 micron. And that indicates that they could have excess cold dust emission, so foreground dust extinction. And this is consistent with the argument that maybe these X-rays emission for these nuclei are actually diminished because of these dust obscuration. And lastly, we also compared the luminosity with the mid-infrared PAH equivalent with, and we see that for the AGNs, there is an overall trend that with the higher radioluminosity, we're seeing lower or diminished PAH equivalent with, and for the and some of the nuclei that are considered composite nuclei or do not have a straightforward AGN identification, they also have these relatively lower PAH equivalent with as well. And so that could indicate, combined with the other evidence, that these nuclei with the highest radioluminosity could potentially be powered by this heavily obscured AGN activity. And these AGN activity could actually be very powerful. It's just that the dust obscuration is also very strong, that we just don't see it. And the radio is basically picking out the non-dust attenuated emission. So another possibility that we have to consider is that, okay, it is possible that these nuclei are AGN but buried, but would it be possible that starbursts can also be driving these elevated emission? Especially in theory, it's been predicted that in this gas-rich nuclear environment of local LIRGs and ULIRGs, there could exist these optically fixed starbursts that's basically solely supported by the radiation that's been dust reprocessed. And so in this model, the determinant factor is, how gas rich it is, and also how fast the stars are moving. And when we when we input these several factors into this model, that we get something that look like something on the right that I'm showing here. And so here with increasing molecular gas fraction, assuming that all the radioluminosity coming from star formation, we have these elevated radio emission as well. And when we compare this model to the symbols or to the points that we have, we see that none of the nuclei actually greatly exceed above these model prediction. So this model prediction, when we, it's basically assuming that all the radio emission is coming from star formation. So we would have expected that if it's completely dominated by AGN activity, it would lie far above the models. But because we're not seeing that, there is the possibility that these nuclei could be powered by this very extreme starburst activity as well. But of course, we would also need, instead of assumptions, if we can measure the molecular gas fraction and also how fast the stars are moving in the infrared, it will be greatly help constrain the model as well. And so lastly, because we've identified these different regions and we've classified them into different types, and we also sample the different merger stages, we can see how frequently these different types appear along the merges. And so here, when we normalize how many galaxies are in each merger stages, we see that at earlier stages and early interaction stages before the galaxy merge, we have more starburst nuclei and also more star formation that's outside of the nucleus. So star formation is triggered earlier in this interacting stages. And then later, we have more composite nuclei and also slightly more AGN as well. And so this basically is pointing to this evolution scenario where the AGN, where the starburst is triggered early on in the merger sequence, and then later they develop into the AGN. Also, when we look at the nuclei and their luminosity in the different merger stages, we see that in the late stage, even though the nuclei span a very wide range in terms of the radioluminosity, we see that on average, the luminosity is raised, and so that the nuclei are brighter in the radio in the late stage mergers, which also combining with the earlier findings that we point out is that these AGN starburst nuclei in the late stage mergers could be representing this phase of rapid host supermassive black hole co-evolution, where when the starburst activity is reached to a certain extreme state, and when it brings a lot of gas in there, and the AGN could be triggered. But this is also when we have a lot of dust obscuration, as shown earlier, where we see the highest, the nuclei with the highest radioluminosity are also more dust obscured and have smaller pH equivalent widths. And so that's basically all I have for the main part. And I'm here for, here I have this summary of what we talked about. Basically, we'll look at the radio emission at different frequency, at different scales as well. In a sample, in a representative sample of about 70 local LIRGs and ULIRGs. And we found that basically on the larger scales, we couldn't really distinguish the AGN from the star formation when we use the radio and infrared correlation. But we could, from the spectral shape, deduce that the AGN is overall at large scales is more dominated by synchrotron emission, and we can see the distinction a little bit better at lower frequency and also longer infrared wavelengths. And also at a smaller scales, on 100 parsec, we're seeing the individual star forming or AGN knots in the very central parsec of these very extreme systems. And we see that all the nuclei, basically, that has some kind of AGN contribution show higher radioluminosity and surface density relative to the ones we know are just star forming. And so these nuclei could be powered by AGN activity or and or extreme nuclear starbursts that's optically thick. And in the late stage mergers, they could be representing a phase of very powerful post-supermassive black hole evolution as well. And before I end the talk, I just want to quickly mention that now that we have, the radio observations on 100 parsec scale, we have these measurements, and we also have JWST data that's already been, published and also coming in, and we can also make some comparisons with infrared on much smaller scales than before. So we cannot just we don't need to limit ourselves on a kiloparsec. We can also dive down into 100 parsec. And so some recent studies have shown that the 15 micron could possibly be used as the proxy as the total infrared emission. And with that, we could compare what we see in the radio to what we see in JWST as well, to see how the radio and infrared emission correlates. And here on the right top, I'm showing that the JWST mid-infrared emission of VV114, the Galaxy I showed at the very beginning, you can see how well the morphology in infrared is correlating with what we see in the radio. And some studies also use the ALMA continuum as a proxy for the dominating IR emitting region. And so that's another pathway that will be interesting to explore. And there are also a lot of archival data on ALMA that we can try to see whether some regions have very high infrared surface density that could be indicating this extreme AGN activity. And for some of the mixed composite nuclei, GWC would be able to give us the mid-infrared diagnostic at much higher resolution and better sensitivity than Spitzer. And so, for example, same Galaxy VV114, it's been shown that in the southwest core, the pH equivalent width at 100 parsec scale is actually very low, even though we don't detect the ionization lines that's directly indicative of the aging activity. And also some studies have shown that at millimeter wavelengths, the ALMA continuum may be able to trace the X-ray, the hard X-ray luminosity that's related to the coming from the AGN. And this is a study that's based on local known AGN. And it'll be interesting to see whether we can find any correlations between ALMA and the radio that we're seeing. And lastly, and ideally, if we can get VLBI observations, then we can then directly look for the very compact parsec scaled high brightness temperature core that maybe exist in these mixture or in this composite nuclei, and also to see whether there's aging signature and to separate the more diffuse, perhaps more extended star forming activity from the very compact aging activity. Yeah, but that's all I have. Thank you for tuning in. Thank you for listening, and I can take questions.
Thank you, Yiqing, for an excellent talk. Are there questions from the audience? Oh, Sarah?
Hi, I'm here with my student, Greg Walsh, who's going to ask a question.
I'm glad she said that because I was going to have to say this is not Sarah. Yeah, so this is Greg Walsh at West Virginia University. The VLBI observations would be a really interesting proposal to put in. Have you already gotten those observations, or are they something you're just planning to do?
Yeah, I'm planning to do, yeah. But I think we do have some VLBI observations for some very small sample of the galaxies. Some of them been published, but I think it would be interesting to look at a larger sample of these composite nuclei just at really high resolution. But if you have suggestions on the frequency that I should go for or anything, I'll be happy to hear it.
Yeah, sure. I'll email you later. Thank you. It was a great talk.
Thank you. Thank you.
Anyone else? Yep.
Yeah, do you hear me?
Yes, go ahead.
Oh, right. Quite a good talk. I just wondering is that you probably know that John Hibbett in the 90s used H1 to work out a evolutionary sequence. I could take it that you're going to have a lot of absorption in the nuclear regions at 1.4 gigahertz, but it would be interesting to extend that work to a higher sample, because I think, if I recall, John used only about 7 or 8. So you have 68. Yeah, H1 aperture synthesis is a lot of work, but presumably you have a lot of students.
Yeah, I think we have quite an amount of unpublished H1 data that someone is working on. But I also know that there's like an ongoing GPT maybe survey that could be coming out soon. But yeah.
Do they have highest sufficiently high resolution, or they're just doing single dish work, just not mapping?
Yeah, there is also mapping. But yeah, we have less people than the amount of work that we have. Yeah.
Yeah, because I know
it will be, yeah.
The GBT has a resolution about 9 arc minutes at L band. So okay, they must be that big.
Oh no,
I
think
doing
we
higher
do have VLA
continuum
data as well.
Oh, it's a VLA too. I see. So
Yeah.
they're using it as zero spacing data. Okay, the GBT.
Yeah, the GBT, I think it's on its own, and it's it's not a mapping project, I think.
Okay, great talk. Thank you.
Thank you.
Other questions for Yiqing?
I have one. If
Yeah.
am I making one?
Yeah.
Hello. Hello. A very nice talk. I just wonder. I mean, when you say that you were in these systems in an evolution phase, and then eventually you might trigger an alien activity. Obviously, to trigger alien activities because you can have a accretion, and it must be a black hole there already, originally for the system to merge. And so how do you look for the evidence of this black hole from the kinematics? The first stage, because if you don't have that, hardly you can trigger any activity.
Oh, you mean gas feeding or inflowing?
Yeah, so you have a kind of
Outflow.
information from the kinematics of the gas in early stage.
Okay, yeah.
You have a concentration of mass, because you don't have that, hardly you can. I think it's more difficult to make the argument you can trigger an AN, although I think it should be probably, but it's an early test. It's a test in an early phase.
Yeah, that's a very good suggestion. I think it will be very interesting to map what the gas is doing for a good sample of them. Yeah, definitely. And I remember that for NGC 6240, one of the collaborators has worked on, looking at the molecular gas, and then they're seeing that the gas is all like concentrated in between the two supermassive black holes in this merger, which I thought that was very interesting. But this is something that I'm definitely interested in pursuing. Yeah, thank you for the suggestion.
And if I maybe add as well, I think this red-infrared correlation, I always have certain suspicion because of the low resolution you are comparing, particularly from infrared. So you might have your radio data in 10 kilopascals. I mean, who knows where is the radio emission source and where the many other infrared emission sources are. Because while Herschel has low resolution, you might get much better, of course, in radio. So now with GMWST, you might try perhaps 70 microns, a very good tracer because it's traced really cold as maybe most of it. But we are not at the resolutions yet there.
Yeah.
But with GMWST, you can push a little bit to see whether nodes in radio correlates with nodes on infrared, mid-infrared, and see fine-tune somehow the correlation, or maybe found it that they correlate sometimes or sometimes not, or depends on the sources you have.
Yeah, that's definitely something I'll be interested in.
Because you can compare,
yeah,
resolutions becomes more closer.
Yeah, definitely. Yeah, and then as you said, like at this very large blobby scale, that basically we see the correlation. It's because everything we're looking at is mostly star formation. So we can't really isolate the very, center, the powerful thing. And the only things that deviates from the relation that we see are already very well known AGN that have already been able to be discovered via other means. Yeah, that's a very good point.
I just want to add a quick comment before I call on Claire. I mean, even in the VB114 case where we have the JWST image and the radio data, I mean, I don't know that those correlate. I don't, even if you can kind of separate some of the sources in the JWST, like they don't seem to me like they would correlate if you can resolve it into different knots. So what's going on? I don't know. Yeah, resolution would definitely be key. Claire?
Yeah, going back to NGC 6240 and its gas kinematics, we were able to identify where the two AGNs are based on high resolution, spatially resolved gas kinematics around the two black holes. And the molecular gas that you just referred to is flowing in between the two galaxies. And it's not, so if you study the kinematics of that, you're not going to learn too much about the black hole. You'll learn a lot about how the two galaxies interact with each other.
So resolution really matters.
Nice.
Actually, a quick note on 6240. You were showing that radio bubble. How often do you see that in the gold sample?
Ooh,
I apologize. The larger, yeah, that one.
Yeah, I think this might be the only one that we can get. So this is also, I failed to mention that this is also a snapshot survey.
Okay.
I wanted to ask if that radio bubble correlates with the X-ray bubbles that are seen in 6240.
I'd be curious about that too, but I think we might have lost Yiqing for another.
Yeah. Okay.
I'll just be sure to relate that message if she comes back quickly.
Thank you.
Thanks, Claire. Yeah, apologies to everyone. I guess I'll.
Is there time for more questions?
Yeah, I think right now the problem is the speaker's internet is not very stable, so she
Okay.
appears frozen on my screen. I think she's probably trying to come back though.
All right.
Oh,
Sorry,
she's back.
I'm back.
So we actually accumulated a few questions for you while you were gone, but
Okay.
one quick
Awesome.
one. Yeah, so one quick one was about the radio bubble, but Claire was wondering how it correlates with the X-ray bubble that we see in this galaxy. And then I think David has another question afterwards.
Yeah, I think I did this comparison before visually, and I can't remember exact, but I vaguely remember the X-ray is a little bit bigger compared to the radio. But I'll have to double check that. Yeah, but this is this is an interesting source. Yeah, I'm definitely interested in following up more with it. Yeah.
And I would say that based on new incoming JWST data that Justin's working on, we're seeing more correlation between radio and other gas bubbles. So we should definitely look more into this. It may or may not be the only source in the mergers. Yeah. Sorry, David, your question?
Yeah, just a question. Is the millimeter continuum strong enough that you might be able to see CO absorption even at at the high, even at high resolution? That may tell you, about inflow or outflows and so on.
Oh, you mean if the gas is
If it's
very concentrated in the center, it will be self-absorbed?
no, I mean, if you have simple, absorption, and if the continuum is strong enough for that, the radio continuum.
Yeah, that would, I guess, that would be interesting to look at. Yeah, we do have, I do have some collection of archival data that I could potentially do this kind of test that you mentioned. Yeah, thank you.
All right.
Okay, well, seeing that we've come to the end of the hour for time, so let's we'll end the questions here for now. Let's thank Yiqing again for an excellent talk. And I think Jeffrey, do you have an announcement you'd like to make? I see that you have jumped in the chat.
Yeah, just for all the students in the channel, we're having our student discussion afterwards as normal. The Zoom link is in the chat and in the Discord. And our speaker is kind enough to join us. So anyone who'd like to join, please follow that link.
Yiqing, if you're able to join, the students would really appreciate it.
Thank you.
I'll be there.
Thank you.
Thank you all for tuning in.
Thanks, everyone.
Yeah,
Thank
all right,
you.
see you everyone next time.
Yeah.
Yep.
Yeah, great job, Yiqing.
Yeah, great.
Thank you.